Disclaimer: this video and all its content were generated by our team solely. There was no external agent or any AI used to generate this video or its audio. Everything has been created in a Python library named Mani for the visual representation purposes. Thanks to our team members, me, Neeraj Parekh, Aditya Bhalika, and Varun Goda. Thank you to our college, MIT Academy of Engineering Pune, and at last, thank you to PC Zoe for organizing this hackathon. Climate smart SAR water monitoring system using Sentinel-1 and ML AI algorithms for flood resilience. The study area of our project is Pune for now. As we know, Pune is a region surrounded by many water bodies and is rapidly urbanizing area where water scarcity is becoming a crucial problem. Over 4 years, we have witnessed dramatic changes, but traditional monitoring is slow and expensive and many times inaccurate. Like in July 2024-2021, 486 mm of rainfall happened in just 72 hours, one of the most extreme events Pune has ever faced until now. Section 2: Problem, Data and Definition. For now, our study area remains to be Pune region, and we will gradually scale to all over India as our project expands. So, for basic details of Pune. Pune is an area surrounded by many different water bodies, but still faces water scarcity. Due to climate changes, the region has been facing a lot of variation in monsoons, like delay in weeks of monsoon. Then sometimes it faces flash flooding, such as a year 2021, where this unprecedented rainfall variability was huge. This data is from the monsoon data of PCMC and Pune Board of Rainfall. So this justifies our problem statement that real-time understanding of the water area isn't optional anymore. It's essential for water security and disaster preparedness. Our goal directly aligns with the UN Sustainability Development Goals. Goal 6, Clean Water. Goal 13, Climate Action. And our solution provides actionable intelligence for policymakers, farmers, and urban planners. But before we dive into our methodology, let's understand why we choose Sentinel-1 C-band SAR data over different radar frequencies that are available in the world. The X-band satellites like TerraSAR X provides pixel resolution of just a few square meters. That is very high resolution, which can be used for monitoring single structures or detecting small unstable areas like landslides or building subsidence. Then comes the C-band satellites that includes our Sentinel-1, which have high pixel density of tens of square meters. This medium resolution is ideal for wide area phenomenon like regional water bodies monitoring, where we need both detail and coverage. The next comes L-band, such as Alos pulsar, that penetrates deep into vegetation, seeing through forest canopies, critical tropical structures, forest areas, but it is less precise for water detection. So here we have the Sentinel-1 SAR image. Notice that the black and white, almost alien appearance is just a radar, raw backscatter image that is clicked by the satellite. It's not a perfect image that is under an optical sensor, but at the right side of it is the Sentinel-2's optical sensor that has familiar colors and identical bodies. But the Sentinel-2 is almost useless during the monsoon season because cloud blocks the views for days. This is why we infuse both data sources from SAR that provides all weather reliability and the optical imagery data that provides contextual understanding of the object we are monitoring, such as water bodies, buildings, and also helps in removal of those particular water bodies. So how does SAR actually create these images? Let me explain through the imaging geometry. Imagine a target area divided into resolution cells. The satellite moves along its orbital path, left, up, right, like it's orbiting the Earth and systematically illuminating each cell. It transmits microwave pulses and measures two critical dimensions: range, the distance from satellite to target measured horizontally along the radar line of sight. This determines the resolution particularly to the flight path. The next is azimuthal resolution. This resolution is along the satellite's direction of travel. This is achieved through Doppler processing of the returned signals as the satellite moves. From Sentinel-1's vantage point at 700 kilometers above Earth's surface altitude, roughly twice the height of the International Space Station, a single image captures an enormous area. This Sentinel acquisition covers across 250 kilometers in width and 400 kilometers in length. That's the whole Pune metropolitan region in a single pass. Wall to wall covers every 12 days of data. The real power of SAR lies in interferometry. Unlike amplitude-only processing, the SAR uses a phase information of radar waves. Every SAR image contains both amplitude and the strength of return signals. The phase. This gives the precise position of the radar wave when it's hit the target and returned. By comparing two acquisitions from the dates between November 2009 and 2010, we created an interferogram. This color-coded map reveals ground movement with centimeter-level precision. This index shows displacement from -6 cm to +6 cm, indicates which has the red, which indicates the ground subsidence, and the blue, which shows uplift. This was taken after an earthquake. The concept of interferometry is borrowed from physics. This LIGO's gravitational wave detector uses laser interference to measure space-time ripples. We apply the same principle with the radar waves instead of lasers. The applications are vast: earthquake monitoring, volcanic activities, infrastructure stability, and yes, water body dynamics, where seasonal flooding causes measurable ground subsidence. Section 3. Methodology. We use optical data and many other different data from satellite, such as Sentinel-1, and optical indices such as NDWI, NDMI, NDVI, the terrain data such as slope, elevation, hydrology reports, and many different references database and maps such as OSM water bodies and government data. This creates a 31-band fusion image that is highly detailed and gives us the exact position of water bodies, and we can track exactly how the water body changes. Our processing includes data acquisition, pre-processing, multimodal fusion, and then using ML to determine and increase our probability of finding the outputs. And then we use the validation phase to validate it with the real-world data of map data, such as OSM water bodies. We are able to achieve across 90% of accuracy up until now, and many water bodies have been detected up until now. The 9-phase streaming pipeline, which processes the SAR imagery. In the first phase, we process the synthetic aperture radar image for removing the noise reduction, the spectral filtering, and geometric corrections. Then we take the area of interest and crop it. Then we do the segmentation phase, where the detection region is grouped and then clustered into many different small subregions. And then we detect the water bodies, urban areas, vegetation, providing detailed spatial context. Then we do the classification using ML to recognize the different patterns of rivers and different land cover classifications. Then we do the post-processing that defines the classification outputs. It provides filtering to remove false positives, smoothens the boundaries, and integrates temporal and contextual data to improve the overall accuracy. Then we integrate and bring together all the different parts. Let's look at our results. This is our processing and filters we applied on the SAR satellite images. These are the different filters, such as digital elevation model, the DB ratio, VH and VV ratio, which are the vertical horizon and vertical type of clicking the image used by SAR satellites. And then we see our final product that is detecting all the water bodies and removed the rest of the materials that is present in white. The water bodies are present in all white. This is the elevation filter and the VH band filter image after processing. This is the next image, which shows us processing of elevation and the processing of the vegetation index. Then the processing of the image in cluster or in parts, which is then stitched and processed to get the final product, which is the water bodies detected. Section 3. Methodology. For our AI/ML processing, we use UNet architecture, which is a gold standard for semantic segmentation. This encoder-decoder structure learns to identify features and make neural networks between them. This skips connection and creates many different connections laterally or parallelly, and preserves different spatial details that are lost during downsampling. This boxes over here shows the different type of data, the different structures of data we have that we use in the fusion, such as NDVI, NDWI, and the SAR images. It creates many different patterns and recognizes the small water bodies that can go undetected. It gives us accuracy of average 90%. This is a matrix representation of how we detect the water bodies. We automate the process by calculating the number of pixels of water bodies that we detect through a certain level of thresholds that we use for cutoff. Then comes the transformer attention model on the scene. We are experimenting with transformer architecture models that do the temporal attention across 12 days with revisit cycle. This learns which month correlates and crucial months that are used more for the data sampling and giving us the data of every water bodies accurately. For real-time prediction, we use echo-state networks. This reservoir computing forecasts water level with minimal overhead. This enables deployment over many different and small devices with lesser capacity. Section 4. Results and validation. The Pune overall year-over-year analysis reveals that 2022 was having the most of the rainfall, and 2024 was having a very low amount of rainfall, which was recorded the least rainfall until now. Let's talk about the rainfall correlation with water area. Over cross-referencing meteorological data, we saw that the detected water extent and cumulative rainfall are closely related. This validates our approach and enables predictive modeling, forecasting water availability from weather patterns. In conclusion, this isn't just a research but a deployable solution for the world's water security. We are already processing the data of Pune area and starting to focus all over India deployment for our project. We want to expand nationwide and integrate this with India's national water mission and provide every water stressed region with affordable and accurate real-time monitoring. Thank you everybody. I am Neeraj Parekh from MIT Academy of Engineering. Moreover, the false positive and the true story is revealed by the confusion matrix that shows that over 90% of our data were positive rate and just over 30% were the false negative rate that were caused by heavy vegetation areas where SAR struggles. This gap is covered by the multimodal fusion that we are using. Then we compare our benchmarks against the competitors. The traditional thresholding that stands on 68%, the classical 79% ML models, and our deep learning stands at 91.2%. That's a 12-point improvement over the state of the art models.